Hey, welcome back to Fat Mama Physics with another video on work and energy. In this video here, we are going to talk about graphs. Ooh, graphs. When you see this equation here, work is equal to Fs cosine theta, we kind of have to assume that the force is the same throughout the displacement. All of the problems that you've been dealing with, the force stay the same. But what if it's not the same? If it's not the same, the force has to represent some sort of average applied force during the whole thing. And sometimes that's very difficult. So what happens when force changes? We need to use a graph in this case. So here I have a graph which force is plotted on the y-axis, displacement is plotted on the x-axis. Notice as the object is moving in the s direction, the force changes over time. So if you can't multiply these two, what do? On a graph, you can get, and yes, if you're thinking about area, you are correct. You can find the area underneath the graph to calculate your work. And that kind of makes sense because you're multiplying the y dimension with the x dimension. Fs is equal to your work, okay? So here I have two problems for us to try. In fact, I will only do the first one. And I'm going to give you a chance to try the second one, example 6, but I will also go over that one in fast play. So let's take a look at example 5 first. Here we have an object. It experiences a force which changes with displacement according to the following graph. The total work done is 1,440 joules. So that's this whole thing underneath this graph right here. This whole thing under here is 1,440 joules. What is the maximum applied force? So that's asking for this F max here at the top. We want our answer in newtons corrected to significant figures. Okay, so we need to look at the area. So since 1,440 joules is the area, let's take a look at this shape. It's a shape of a triangle, and we know that the area of a triangle is base times height divided by 2. In which the base here is the displacement here, and we read 24 meters. The height is up here, which is our F max. We don't know what it is. All of that divided by 2. Here we have an equation. So I'm just going to rewrite this a little bit better so you can see that. Okay, and we want to solve for F max. To do that, let's times both sides by 2. And next we divide both sides by 24. And multiplying everything out, we get 120 newtons. Okay, so here we have it. The area underneath the graph represents the work, and of course, if you write down the equation and divide it by one of the dimensions, you get the other one, which is your force. The next problem, example 6, is a little bit more straightforward, in which here you have a force displacement graph, and all you need to do is to find the total work done on the object, so the total area underneath that graph. Here's a good time to pause and for you to try the problem. And now it's my turn to do the problem. To get the total work done, we need to find the area underneath the graph, in which we can divide it into two pieces. First piece being a rectangle, second piece being a triangle. The rectangle is length times width, in which the length is 20 meters, the width is 100 newtons. Base of the triangle, don't forget, is the difference between 30 and 20, and the height being 100 newtons, giving us a total of 2,500 joules. Okay, so here are the solutions. So here we have to find the area, in which if you do not know the area of a trapezoid, which is just the top length plus the bottom length, this over here. Sum of that divided by 2 times the width, which is just the height here in this case. If you didn't know that, you can always break this down into two segments, which I chose area 1 as its rectangle, and this triangle here, which I label as area 2. So then the rectangle, we have length times width, and the triangle equation we have from the previous question, base times height divided by 2. We add them up, giving us a total of 2,500 joules. Okay, so something for you to be aware of when you are dealing with problems, that the area underneath a force displacement graph gives you work. So hopefully you learned something in this video that you can apply in your problems. Thank you for watching, and Fat Mama Physics signing out.